Good evening, my favorite OChem 2 class. How is everyone? I am so excited. This entire video is just one reaction, the Strecker reaction. This is an oldie but a goodie. We're talking the 1850s for this one, and believe it or not, it is still used today. This reaction is how we're going to make amino acids. It is literally still used today. It is dirt cheap. It is the ultimate in multi-component reaction. We've already seen some multi-component reactions. In fact, one of my favorites is the Mannich reaction. We saw that back in Unit 3 even. We saw that back in Unit 3. Our Strecker reaction is very similar. We are just building on our concepts from Unit 3 and Unit 4. I can't wait because it looks so complicated, yet it's really important and actually very straightforward. So I love it. It's a great way to end the semester. We've only got one more video after this, and that's when we take these amino acids and we link them together and we make peptides and proteins. I can't wait. So our Strecker reaction has actually been around, again, like I said, since the 1850s. It is a classic multi-component reaction. It's funny because I've actually read the original paper to this reaction. My first career in industry was as a peptide chemist, and my company made amino acids. I actually made peptides. That's our next video. But I was actually offered a job, sort of half serious, half in jest. I could name my own salary if I could do the Strecker reaction enantio selectively. It was a really fun conversation. But as you'll see through our Strecker reaction, that just wasn't possible and actually keep the Strecker reaction. So let me show you what the Strecker reaction is. It is phenomenal. I love it. All right, so our Strecker reaction is actually going to be really similar to our Mannich reaction. So it's great that we're going to do this second. So we are going to start with an aldehyde. What? That looks familiar, right? All right, let's start with an aldehyde. And then we're going to go dirt cheap mixture. We're going to add cyanide. And we're going to add ammonium chloride. Okay, all of these things we've seen before. And what is the secret to a multi-component reaction? Just like with our Mannich, it all has to do with your rates. Your rates of those reactions and those reactivities. You have 3 possible reactants in your system. In order for you not to make chaotic road tar, you have to have 2 of them reacting faster than that third one, and the first 2 have to give you a nice reactive intermediate for that third one. So if we were to look at our KCN, our ammonium chloride, and an aldehyde, what in the Sam heck is going to happen first? Well, first things first, our cyanide actually is in acid. So I am going to also write HCN is going to be present. Okay, now let's just pump the brakes for a second here. Like I said, I've literally read the original Strecker reaction paper, and what's fascinating is they put a little star in their text, and then they refer you to the bottom of the page where it says, please do this reaction outside. And let me just tell you, their scale was on the kilo level, which means they literally were doing buckets full of reactant to make these amino acids. So that is an awful lot of cyanide And as safety standards have evolved, so has our whole system of doing reactions like this. Just standing outside is not okay anymore. You want to make sure, especially since you're generating HCN in this process, that you are in a well-ventilated hood and you're keeping your amounts to a reasonable level and you're making sure that that hood is working and so on and so forth. So if we take a look at our reactive ingredients, that ammonium chloride, we've seen that also in our amines and our imines. So let's put little air quotes there. That's also ammonia. So these two we saw in Unit 3 as a recipe for an imine, and these we saw in Unit 4 as our cyanide is a good nucleophile and our cyanohydrin. Okay, so which one wins? Which one is the faster one? Actually, our imine wins. So we're going to do that first. So the first thing that happens is our aldehyde and our amine form. Oh, let me put that H in there. Okay, we are about to make this imine, but of course we're in slightly acidic solution, so we are going to leave it as the iminium ion. Okay, now isn't this looking familiar? Let's just pause for a second. So far, this is exactly the Mannich reaction. Didn't we form that iminium ion first? Okay, then in our Mannich, we had a nucleophile, and it was an enol. Okay. Now, in the case of our Strecker reaction, we just swapped our nucleophile. Now we have cyanide. So we have cyanide present as either HCN, which this could be the H from HCN, and now we have that cyanide present. That is an excellent nucleophile for an iminium ion. This chemistry I've personally done, and it works very well and very fast. Okay, so now what did we just make? Let's color code for a second here. Let's make that, like that, and we just added cyanide. Okay, so the second part then of our Strecker reaction, we make this kind of version of a cyanoamine. Now, don't Google that because I kind of just made that up. But what we are making right here, okay, let's just picture that. We just made that. Now we know from our Unit 4, shut the front door, what happens to a cyanide if I either use an acid or a base hydrolysis. All right, what happens to your cyanide? You now just made the carboxylic acid. And this, my friends, is our amino acid. I love it. So I didn't draw the full mechanism for this one. I don't have to. We've already drawn it this semester. This first half is an imine. Okay, that's a nice equilibrium of form that iminium ion. As soon as you form that reactive intermediate, here it is, reactive intermediate, now your cyanide can add into that iminium ion. And then we've got a little acid and water we add to that. All of this is in the same reaction and in the same reaction pot. And now what do? You hydrolyze your nitrile. We just drew that mechanism in our Unit 4. So let's mark that. That is our Unit 4 mechanism. All we did is combine them. And in fact, just like our Unit 3 Mannich, the only thing we changed was that nucleophile. So this really is like 3 for the price of 1. We've seen every part of this Strecker reaction. That's what's awesome. So this is literally a dirt cheap, very easy, very green, other than the cyanide, way to make amino acids. And what is the definition of an amino acid? Okay. Well, we have an amine, nice basic functional group, connected to a carboxylic acid. And we have all kinds of functional groups that can go right here on that R spot. Okay, now we recognize that term amino acids to literally building blocks in our body. These are the backbones. If we connect them, we can make peptides. That's our next video. And proteins. They are connected through an amide bond. Our amino acids in life for us, we have 20 amino acids. There are more that are unnatural, but there are 20 natural amino acids that we need. We need a combination of those in our proteins. If I'm not mistaken, again, I'm a little far away from my biochem, so you may want to check that. We have 11 that are non-essential, meaning we can make them in our bodies, and 9 that are essential. Again, you're going to want to double check those numbers. You have had some biochem a whole lot closer than I have in my fun little tidbits for our amino acids, but that means that we actually have to eat these. Okay, so we've got some that our body can actually make, and then the others we have to literally eat them in our food, in our proteins, and then we need to hydrolyze that amide bond and use those amino acids in our biological functions and in order to use them. So this is our definition of an amino acid. So has anybody made the connection yet that you literally have an acid and a base sitting right next to each other? So let's draw that out. All right, for funsies, I stole this from Wikipedia, but I also put that reference up here. So let's give them a little bit of street cred. I'm giving you a bunch of web links again. This is just the amino acids table from Wikipedia. The reason I like it is, let's take a second for some tidbits on our amino acids. Amino acids have obviously been around for quite a while, and we need them, and they're an integral part of our biology and our biochemistry. And so they actually over time have developed several names for them. So I love this one because they're grouped in the type of functional group that our group is. But they also show the name, the code, and the single letter code. So each amino acid actually has 3 different ways to designate that amino acid, and they each have a name, they have a 3-letter abbreviation, or a single letter abbreviation. So depending on the classes you're headed to after this, if you're headed to your biochem after this, you likely are going to have those memorized or in a table somewhere so that you can figure out, your strung along amino acids in your chains. And I actually worded one of your questions like that on your take-home exam. I used those little codes. So before you get upset with me, I also just gave you the table with the little codes, so we're good. Okay. So this is an awesome one. This is, like I said, just from Wikipedia. Look at all those different R groups, and then look at the fact that you have a stereocenter. What? We are coming all the way back to OChem 1. All of our amino acids except glycine have a stereocenter. Isn't that awesome? So I want to take a little bit of time actually with our amino acids and just give you some history, and then I want to show you how to draw them with those stereocenters, because again, amino acids have been around forever. So this is just a little bit different than what we learned in the beginning of our OChem 1 with our stereocenters, because we have a whole lot of history before anybody even knew how to designate those stereocenters. So just as a quick reminder, our RNS system really didn't come out until the 1970s, but people were obviously studying, using, building, making amino acids for a couple hundred years before that. So we are going to have some vocab there. Okay. All right, so amino acids have a rich history. This is actually an experiment that I heard from a geology colleague, and that is the Miller-Urey experiment. If you've had some geology, I think you've studied this. If you haven't, I just wanted to share this link. This is just fun tidbits for the end of the semester. What it is he actually wanted to recreate what would be the idea of a primordial soup. And so if he literally took a flask in the lab and he put together all kinds of water, nitrogen that was in the atmosphere, things that he thought would be, okay, what was in the atmosphere at the time, carbon dioxide and so on, methane. Let's put all of that in a flask and then literally let's zap that sucker with lightning and let's see if we actually can make amino acids. So this is one of our theories in evolution and the Big Bang Theory, is that literally lightning struck that primordial soup and amino acids started, and that was the formation of amino acids. And it's actually really fascinating. You should check out the link, because indeed he did make amino acids by passing a current through that cauldron of gases from the primordial soup. So it's actually pretty interesting. What's cool about it is that it was just updated a couple of years ago. Those experiments started in the 1950s. Actually, if I'm not mistaken, it was 1952 that he published those experiments. But back about 10 years ago, they went back in to kind of catalog and organize his lab for whatever reason, and they reevaluated his samples and actually had found quite a bit more amino acids. He had reported the 11 amino acids that he found. They found even more. And what's fascinating is that in his experiment, all of the amino acids that were made were racemic. So there's still mystery alive with our amino acids. They, in fact, were racemic in the lab, and now that has been updated as well. So it's really pretty fascinating. So check it out. There's a fun link for the Miller-Urey experiment there. And then because our amino acids have been around forever, also in the 1800s, thinking about that structure of those molecules and literally thinking of sugars. So Fischer projections, I believe it's Emil Fischer, started with basic glyceraldehyde. And starting with glyceraldehyde as the most basic sugar, recognized that there were two forms of that basic sugar, and then grew a way to draw those sugars. Wrong pen there. So looking at a way to draw that 3D structure of sugars, came up with this Fischer projection. I know you've seen them in textbooks before, but you may not know where they came from or why we give a crap about them. So I want to treat just amino acids with a Fischer projection. So when we think of an amino acid, we have a tetrahedral carbon in the middle of that amino acid. And that is nice and sp3. Inherent in all but glycine, we have 4 different groups in that amino acid. That means that we can have enantiomers. We have a stereocenter right there at that connection of that amine and that acid. So we know now, since the 1970s, we assign RNS, but that is the most modern. That is the only one that tells us literal arrangement in space. Okay. But with that arrangement in space, you know, again, our amino acids have been around forever. So how did scientists figure this out beforehand? And it turns out Mother Nature prefers certain arrangements over the other one. So how do you designate that? So for a long time, the language of amino acids was D and L. Okay, and you're still going to hear that. And this is a big D and a big L. So this is the older version of that 3D arrangement. And this only works for amino acids and sugars. Let me show you why. We're going to follow a set of rules, and we're going to draw it like a little cross mark. Okay. Our set of rules is that we will always put the carboxylic acid on the top, and we will always put the R group on the bottom. And now what's going to designate the D and the L for us will be where the nitrogen ends up. Okay, so then our mirror image, again, keep your carboxylic acid on the top, your R on the bottom, and how you have an enantiomer is that nitrogen is on the other side. So this only works because you always have two groups that are the same. So you can have a set rule for which one goes where, and that's where this designation is. All right, so if our nitrogen is on the right, this is D, and if our nitrogen is on the left, that's L. And it turns out that nature prefers the L. Isn't that fascinating? But you're thinking, Dr. Amorti, this is a crackpot way to look at this because this looks flat. Doesn't that look flat? Well, what the Sam heck? We know they're not flat. So how do you actually picture a fissure? This is the weird thing. So the ones, whoa, what did I do? Okay. So our groups that are on the line this way, or our horizontal bond, that is actually coming out at you. So let me draw that. Okay. Our actual horizontal, like this, is really bold. So that means that your hydrogen and your nitrogen are literally coming up at you, and your CO2H, that carboxylic acid, and that R group are coming away from you. So it's a really funny way of looking at your tetrahedral. It's not the normal tetrahedral that we look at with our model set. You're still going to model this, but you're going to turn it. You know, how we typically like to look at it is show that 109.5. We keep two flat and we have one bold and one dashed. But back in the day, this is how they would view that model set in 3D. So I think it's pretty fascinating that in nature, we actually prefer one over the other. But again, that doesn't always tell you what it looks like in space. For other molecules, the only reason this works is our amino acids have two groups that are always the same. So you swap two and you always have the enantiomer. So that's why this system works. Now, keep in mind, that's a big D and a big L. That is not little d, not little l. That is how we rotate light. Okay, those are two different things. You see the same thing in sugars. You have a D and L in your sugars. All right, isn't that awesome? So we've got one more little tidbit with our amino acids. Those of you heading to biochem, you're going to get tortured by this. I'm just going to define it and then end there, but you'll keep going. So let's tackle that question again. Wait a second. Shut the front door. We literally have a base next to an acid. Okay, you have learned in the last 2 years of chemistry that the fastest reactions known are acid-base reactions. And, sweet Jesus, if you want to make it even faster, you have them connected. We've learned that in the last 2 years of chemistry as well. So you have a base next to an acid. So our amino acids typically sit as something called a zwitterion. So for some reason my pen just keeps quitting on me and I have to just plug it in real quick to my iPad. I don't know why. I'll give you 1 second here. So our amino acids, they sit literally as those 2 charged species. So what just happened to our nitrogen? Now it's protonated. So when you have your base literally taking that hydrogen and leaving behind that conjugate base, this is called a zwitterion. You rarely have 2 charges in the same molecule, let alone a plus and a minus just sitting there next to each other. That is very rare. So this term zwitterion, this is the only time you really see that is in amino acids. Now, why you're going to get tortured by this in biochem? Because this is pH dependent. So you're going to go crazy with all of your pH. All of your nice logarithmic looking curves with pH and looking at what's protonated and what's not. And you're going to have a whole lot of fun with that in biochem. We're not going to come anywhere near that in this class. We're just going to define zwitterion. Isn't that awesome? All right, so I want to summarize this whole thing with a take-home message. We just kind of had some fun with our amino acids, but let's go back. We only did 1 reaction here, and that was our Strecker reaction. So if we have 20 different amino acids, and again, we're sticking to the standard ones, we're sticking to the natural ones. If we've got 20 different amino acids, is it possible to make them from the Strecker reaction? And how do we do that? Well, let's go back here. And what are we actually... my pen is having problems again. Hang on. And what are we actually putting into our synthesis? Well, we've got an amine. Where is the amine coming from? Okay, hang on. Let's track our stuff. Okay, so what turned into our amine? Let's color code. That's coming from that ammonium chloride. Okay, so no variation there. All right, the actual acid is coming from the cyanide. Okay, awesome. That's not our R group. Where is the variation coming from? The aldehyde. So all of those amino acids, shut the front door. Let's take something like right here on the bottom. Let's take our valine. And let's look at that amino acid. All right, we've got an amine. Now, I'm not drawing per particular stereocenter. I'm just drawing my tetrahedral. Okay, then if this is an isopropyl, okay, then the only thing we change out of this whole synthesis is that starting aldehyde. So that means we start with this. There is our R group. And then we add our KCN and our ammonium chloride. Done. And now you just made your valine. Isn't that incredible? So out of this entire thing right here, how easy is it to make amino acids? You find your side chain, whatever is that R group, and it literally has to be on your aldehyde. That's it. So I've got this in your take-home exam too. I'm going to ask you to just dealer's choice. pick 3 amino acids you feel like making, and then just show me what those starting materials would be. Isn't that fun? We'll take a look at that on Zoom tomorrow, and we'll do some of those problems together. So just keep in mind, how are you actually going to use your Strecker to make any kind of amino acid, whatever your R group is in your aldehyde, is going to end up with that R group in your amino acid. Look at that. Okay, so again, this looks so fancy. Holy cow. Draw that mechanism out for your friends and you'll impress them. But at the end of the day, all you're doing is swapping the R group on your aldehyde, and you can now make anything on that table. Isn't that incredible? It's almost like we should put that into a take-home exam. What? We did. It's posted on Blackboard for you. All right, so I'm going to stop this video, and then our next video is going to be stringing these amino acids together.